Hello, we're going to talk about motion and acceleration. First, I want to go back to what we did in lecture on Tuesday, um, and talk about how we, um, what to do when the motion isn't moving at a constant velocity, or when velocity isn't constant. So what you do is you still look at the slope. So here, the slope is first, it's negative. So, okay, that means velocity needs to start below zero. And then it goes to zero here at this point A. And then it slowly starts to increase again until we reach the origin position again where x equals zero. Apologies for the cat. That is blurry behind me. Anyway, so this is where the slope is the maximum. So at point B, we should have the largest slope, and then it's going to slowly start to decrease until it gets to zero at point C. So what this would look like for a velocity graph is like this. So the velocity initially is below zero because we saw here the slope was negative. But then at point E, it is zero. So it should cross the origin on the velocity graph. And then point B is the maximum slope. So that's the highest point the velocity gets to. And then, as I said, the slope slowly starts to decrease. So that means velocity is getting smaller. And then at point C, it's zero again. And you will see in a couple moments why I am bringing this up. But this is an example where the velocity isn't constant in our graph. And there was one graph from Tuesday where that was the case also, but we didn't spend a ton of time with it. So anyway, I wanted to show you that. And then I want us to think about this example of we have a Chevy Corvette and Sonic. And if we think about how long it takes each of them to go from 0 to 60 miles per hour, the Corvette can do it in 3.6 seconds, and the Sonic takes 9 seconds. We can see this also in our particle diagram of the situation. In the same, or I guess the same amount of time, that it takes the Corvette to get all the way up to 60 miles per hour. We can see that the Sonic did not get nearly as far, and its velocity vector is much smaller. But what is happening here is the rate of change of the velocity is different between both of these. We can also look at what this would look like on a velocity graph. And this is an example of velocity graphs where velocity isn't constant, it is changing. And so we can see that the Corvette has a much steeper slope than the Sonic does. And we saw that it's changing faster than the Sonic is. But what is this? What is the slope of this line? What does it represent? This is acceleration, and acceleration is just the rate of change of velocity. So think back, velocity was the rate of change of position, also known as displacement over time. And now acceleration is the change of velocity over time. So part of why we started out talking about a non-constant velocity graph is we can do the same thing with a velocity graph, or we can get an acceleration graph the same way we've gotten velocity graphs from position. So if we have this velocity graph, for example, so we have these two segments where we have changing velocity, and then we have this segment here where velocity is constant. And acceleration is just the slope of the velocity graph. So we can't with this graph because it didn't actually give us numbers, but if we had numbers, we could get a value for the slope of this segment, and then we would plot that on our acceleration graph as the acceleration for that segment. And then we have a flat line for this segment. And so that means that the acceleration is 0 there. And then here, the acceleration or the slope is negative. So the acceleration is also negative. So that we would graph that below the 0 axis. So the sign of acceleration is not as straightforward as with like position and velocity, where position, if it's on the right of the origin, it's positive. If it's on the left of the origin, it's negative. And velocity, if it's moving to the right, it's positive. And if it's moving to the left, it's negative. But acceleration, the sign of it depends on also the I'm sorry, I lost my train of thought. It also depends on what direction the velocity is going. So in this example, we have an object moving to the right. So we can look at our particle diagram and see that the velocities are all moving to the right. And it's speeding up. And so because it's speeding up, that means the acceleration vector should be in the same direction as the velocity vector. So general rule, speeding up means the velocity and acceleration are in the same direction, meaning our acceleration here is positive. And then we can see on our velocity graph that that means we have a positive slope. In this example, the object is moving to the left. Again, look, our velocity vectors point to the left. So the velocity is negative. And we're told that the object is slowing down. So what we see here is our velocity vectors to the left and our acceleration vector to the right. And this means that even though our object is slowing down, our acceleration is positive because our object is moving to the left, which means negative velocity, and it's slowing down. So acceleration and velocity are in opposite directions. So we end up with positive acceleration. And then back at the graph, we see that this is a positive slope still, because then that's good because acceleration is positive, but it's below the 0 line because the velocity is negative. In this example, we have an object moving to the right again. So again, here is our velocity pointing to the right, and that's positive. And then in this case, it's slowing down. So slowing down means acceleration and velocity point in opposite directions. So here we have, again, velocity pointing to the right and then acceleration pointing to the left. This means acceleration is negative because it's pointing to the left. And we can see, again, in our velocity graph that it's above the 0 line, which is good because we're, the velocity is positive. But then the slope is negative, which is related to the acceleration, and the acceleration is negative. And then this last example, we have our object's moving to the left, so velocity is negative. This time it's speeding up. So when an object is speeding up, the velocity and acceleration are in the same direction. So acceleration is also negative because it's pointing in the same direction as velocity, and velocity is negative. And then looking at our graph, it is below the 0 line because the velocity is negative and the slope is negative, which makes sense because the acceleration is. Here's all of these together. I'm going to skip this. You can look back at it. What's important is how the process of finding the sign of acceleration. So in order to find the sign of acceleration, you need to know the direction of the motion and the direction of the velocity. And then you need to know if the object is slowing down, speeding up, or moving at a constant speed. And then you also need to know what that means for the direction of velocity and acceleration. And here's what it means. Slowing down, velocity and acceleration are in opposite directions. That acceleration is what is causing the slowdown, and it needs to point in the opposite direction of the velocity to do that. Speeding up, they point in the same direction, and that is how the velocity increases. And then the velocity is constant. That means the acceleration is 0. Now, we're going to get into some kinematics equations. So let's start out with the position of an object in uniform motion. Uniform motion means there's no acceleration. So this really just comes from, just look here first, it comes from our equation for velocity, the displacement divided by the time interval. If we expand these both out, we have x final minus x initial, t final minus t initial, and then we can rearrange things a bit, like this. We actually want to write it as, so look at the black first before looking at the pink. The velocity equals the final position minus the initial position divided by the time interval. And then if we multiply the time interval on both sides, we get this here where it's the velocity times the time interval. And then finally, we can add the initial position to both sides. And that's how we end up with this equation here, where the final position equals the initial position plus the velocity times the time interval. And again, this all comes from our definition of velocity. So this equation only works when there's no acceleration. And this, and now, now we're moving on to constant acceleration. And this looks like a flat line on the acceleration graph, which is just like what we saw when we had constant velocity on the velocity graphs. And our velocity graph, for at least for this acceleration graph, would just look like this. It's definitely possible for velocity to change, for the slope to change, and then we have like the step graph like we had for velocity. So looking at velocity with constant acceleration, we start again with this time with our definition of acceleration, which is the rate of change of velocity or the change of velocity over the time interval. And we can just expand the velocity term. So it's the final velocity minus the initial divided by the time interval. And we can multiply the time interval on both sides and then add the initial velocity to both sides. And we get this equation, or this one here, which is the final velocity equals the initial velocity plus the acceleration times the time interval. Sorry, also, I should have said this the previous or 2 slides ago, but just to be clear, I do not expect you to be able to derive these equations. I am showing you where they came from, so they're not some like magical mystery thing. And also it can be really helpful for some people, but I do not expect you to be able to do this on your own. If you can, that's awesome. If you can't, don't worry about it at all. You need to be able to use these equations. And I don't want them to be some magical mystery where you don't know where they came from. So this is where they came from, and that's that. So this one works for constant acceleration. If there is acceleration, then you can figure out what the velocity is after a time interval. And if you have 0 acceleration, you'll see, oh yeah, the final velocity equals the initial velocity because it's not accelerating, it's constant velocity. Next up, position with constant acceleration. So this time, where this equation comes from actually has to do with the area under the curve. So like what we did to find the displacement. But then we are also kind of bringing in some other things. So the rectangle, so we have, it's divided like this rectangle down here, and then this triangle. And the rectangle is just the velocity, the initial velocity, because that's what this point is, times this time interval that we're looking at. And then the triangle, because a triangle is 1/2 base times height, so that's where we have 1/2. Excuse me. And then it's the change in velocity, which makes sense because we go from initial to final. That's the change in velocity. And then it's multiplied by the same time interval. So that's like the easy part of it. And then we add complications. Really, we substitute in for the change in velocity, the acceleration times the time interval. That also just comes from the acceleration definition equation. But it makes our triangle term 1/2 the acceleration times the time interval squared. And the area under the curve is the displacement. Displacement equals the area of the rectangle plus the area of the triangle. So displacement equals the initial velocity times the time interval plus 1/2 the acceleration times the time interval squared. And what we'll usually do is have this equation expanded out to separate x final and x initial. So normally maybe you'll know the initial position and you want the final position. Also, I call this the long kinematics equation. I mean, you can see why it's longer than the other one. And yeah, that's where it comes from. It comes from area under the curve or area between the graph and the origin or zero line, and the definition of acceleration. And last one is velocity and displacement with constant acceleration. And this one also starts with the acceleration equation. This time you can solve for the time interval, which gives you the final velocity minus the initial divided by the acceleration. And then you can plug those that are this fraction into the displacement equation for the time interval. I'm not going to show you that algebra because, like I said, we don't need to be able to do this. We just need to have some idea of where these come from and then be able to use them. So the equation we get, if you want to do the algebra, you are more than welcome to. But what it results in is the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. So this gives us our 4 kinematics equations for constant acceleration. And really, this one is for, well, I guess zero acceleration is also constant acceleration. But this one only works when you have zero acceleration. The rest of them work with constant acceleration. And again, this one I call the long kinematics equation. So you're definitely going to want to refer to this slide. These equations are also in the equation sheet on Canvas. And yeah, we're going to be using these, and I'm gonna on the next slide, I'm gonna just walk you through how we start out with the process of kind of breaking up one of the word problems and then how we think about the equations in relation to that. So let's take a look at this problem. It says, as you drive your car at 15 meters per second, which is just a bit under 35 miles per hour, you see a child's ball roll into the street ahead of you. You hit the brakes and stop as quickly as you can. That was weird. In this case, you come to rest in 1.5 seconds. And the question asks, how far does your car travel as you brake to a stop? So let's go through and pull out the important information. First thing, you're driving at 15 meters per second. What that is giving you is your initial velocity. And then you see that you use your brakes and stop. That means that your final velocity is going to be 0 because you're coming to a stop. So we have an initial and final velocity. And then we also see that it takes 1.5 seconds to come to a stop. That's a time interval. And in physics, when we're solving these kind of problems, and honestly, it works for other kinds of problems too. So we break things up into what we know, what we don't know, or what we need, and the equations that we have. So like I said, we know the initial velocity of 15 meters per second. We know that the final velocity is 0 because we come to a stop. We know that the time interval of that is 1.5 seconds. And I think those are the things we know. We can also say that our initial position is 0. We can say when time is 0, like when we are seeing the child's ball roll into the street, time is 0, and that's going to be what our initial position is also. And what we're looking for is the displacement because it asks how far your car travels as you brake to a stop. So that's what we're looking for. We don't know what our acceleration is, other than we know it's negative because it's, or at least in the opposite direction of our velocity, because we're braking to a stop. So to slow down, they need to be in opposite directions, but we don't know what it is. And then we can look at our kinematics equations. So let's do that really quick. So this first equation doesn't work because that's for constant acceleration, and we know there must be some acceleration because we change velocity. Okay, we have our final and initial velocity and time interval, so we could find acceleration from this equation. It's not what we're asked for, but we might need it. Let's look at the long kinematics equation. So we don't have the final velocity, and we do want that because, I mean, we want the displacement. I'm sorry, I said final velocity. We don't have the final position. We want it because displacement is the final position minus the initial position. We have the initial velocity, we have the time interval, we don't have the acceleration, and again, we have the time interval. So this one, we have two things we don't know. This one, we only have one thing, but the thing that we don't know is not the thing the question is looking for. And then this last equation, again, we know initial and final velocity. We want the displacement, and we don't know the acceleration. So we can't use this equation because there are two things we don't know. And the same is true for the long kinematics equation. We don't know the final position, and we don't know the acceleration. So we can't use either of these equations, at least not yet. We need to find the acceleration first. And to do that, we can use this equation here because there's only one thing we don't know, and that's the acceleration. So this is the process of working through, or initially looking at these problems. And we will practice this more. And I will run through this on the board for you and everything. But I wanted to give you a taste of what that looked like. Since you were introduced to these kinematics equations, this is how we use them. We go through, write out our knowns and unknowns, and then figure out which equations work with what we know. And again, in order to solve an equation, you need to only have one thing you don't know. But we can solve these problems with more than one equation, which is what we would do to solve this one. We would again solve for the acceleration from this equation because the only thing we don't know in it is the acceleration. And then we could plug that acceleration into one of these two equations to solve for the displacement or the final position. Anyway, that is all for this lecture. I hope you have a great day.